Hey everyone. So this video I'm going to be talking about the Michael reaction. So Michael reaction is very similar to all the reactions we've done up to this point, like the aldol reaction or the acetoacetic ester or the maleic ester synthesis. In this case, you're going to have a dicarbonyl compound. You're going to have a compound that has more acidic hydrogens than the other ones. And you're going to react that with a alpha beta unsaturated aldehyde or ketone. And so it's like a mixed aldol reaction, but instead of adding, so you're going to have one compound that has much more acidic hydrogens than the other one, so it can be successful. But instead of adding to a second instead of adding directly to the carbonyl of the second molecule, it'll add at the beta position, so you get conjugate addition. So it's like all the reactions we've been doing, but instead of direct addition, it's conjugate addition. So that's why it makes it a Michael reaction. So let's go ahead and look at an example of that. So I'll go ahead and draw my acetoacetic ester. I'll draw an alpha beta unsaturated ketone. So here's the alpha position, here's the beta position. So that's why it's known as an alpha beta unsaturated ketone, because you have that double bond there. And so you can add that molecule to the alpha position. I'm going to go ahead and draw this out. And so here's my alpha position. And so it attaches to the beta position here. So that'd be a CH2, CH2, then my C double bond O, CH3. Okay. And so I did a condensed structure there. If I did a line structure, I'd say CH2, CH2, C double bond O, CH3. So it looks something like that. So here's my alpha position, here's my beta position, so you can see that added to the beta position. Now another thing I could do, just like with the acetoacetic ester synthesis, I could heat that up with acid, and so if I did that, the acid would hydrolyze that to carboxylic acid, two away from a carbonyl compound, and so I'd have C double bond O, and your CH2, CH2, C double bond O, CH3. So here's my alpha position, beta, alpha, and then my second carbonyl. Okay? Let's go ahead and look at the mechanism for that reaction. So just like with all of them, my base abstracts the alpha proton. And then I have my alpha beta unsaturated aldehyde or ketone. So it's going to add to the beta position. Okay. So add to that beta position. So this enolate ion stabilizes the resonance. You can put your minus charge here as well, but then it's going to be stabilized with that carbonyl. So then you have some kind of a proton source that forms a carbonyl, and this will take off that proton source to get your product. So let's go ahead and look at an example. So it says how much you obtain the following compound using a Michael reaction. The first thing I want to do is locate where I have two carbonyls at, because I know where I have two carbonyls where I only have one carbon in between them. So here's one carbonyl, but then it goes carbon-carbon, so that can't work for my dicarbonyl compound. But if I look at this one, here's a carbonyl, carbon, another carbonyl. So that's going to be my dicarbonyl compound. So I'm going to attach something in between. So that's where I'm going to take off this compound. So that'll be my starting material. And then I have this CO2 ET. Now here, if it attaches to the beta position, this must be my beta. There's my alpha, there's my carbonyl. So I have beta, alpha, and carbonyl, so I know it was a Michael addition that way. So there's the two compounds that I need, and then I'll just treat that with a base and I'd get the Michael reaction. So let's go ahead and look at some problems from the textbook. This is what product would you obtain from a base catalyzed Michael reaction of 2,4-pentane dione with each of the following alpha, beta, unsaturated acceptors. And so two, 4-pentane dione, so 5 carbons, 2, 4, okay, with 2 cyclohexenone. So cyclohex is a 6-carbon ring, hexene, so I double bond, so cyclohexenone. So cyclohexenone would be a carbonyl on my 6-membered ring. Then that's going to be 1, so then at 2 position I have a double bond, give me 2 cyclohexene. So another way to name it would be cyclohex-2-enone. Okay. And so the product of this reaction draw out my 2,4-pentane dione. Here's my alpha position. Here's my beta position. So I'm going to attach to the beta position. So if it's attaching to the beta position, that must be my alpha position. And so then the position next to the alpha would be my carbonyl. So there would be the product of that reaction. How about propene nitro? So nitrile is a C triple bond in propene. So nitrile C triple bond in prop is 3 carbons. There's only one place to be a double bond if it's propene nitrile. So again, I would draw out my 2,4-pentane dione. Now it's going to attach. Here's my triple bond instead of my C double bond O. So here's my alpha. Here's my beta. So it attaches to the beta position. So I'd have CH2, CH2, CN. Okay. Is that okay? go ahead and look at 23-17. So what product would you obtain from a base catalyzed microreaction of 3-butene-2-one? So bute is going to be 4 carbons, so 1, 2, 3, 4. 2-one, so 2-one, double bond. 3-butene, so 1, 2, 3. So this time, this is going to be my Michael acceptor, and so these will be my dicarbonyl compounds. So I'll draw this one out. Okay, it's a malonic ester here. And so look at the alpha position between the 2 carbonyls, and I attach to the beta position here. So I'd have a CH2, CH2, C double bond O, CH3. Here's my 2 carbonyls here. So this is the alpha position, so that's what we'll attach to my beta position of my acceptor. So again, it'll be the CH2, CH2, C double bond O, CH3.